Okay. Again, it's nice to have Mete Atature here for one day. It's flying out to London tonight. Mete is actually familiar to faces here in the Boston area. He got his PhD, BU. That's the reason why it says HQOC ITAMP Joint Center of Boston. That will offend a few people in the audience and elsewhere as well. After BU, Mete went to Liège to work with Atature, who was also here before the time. And then in 2007, he went to Cambridge. First started as a lecturer, and then a reader, and now a professor of physics, Cavendish Lab in Cambridge, where he has made a name for himself, the spectroscopy of the color centers in the diamond, using quantum dots, spin measurements, and what he's going to also describe for you in photon interactions. But what also strikes me as interesting is that he works with others in a group, Cavendish Lab, with a very cute name called AMO Physics. Does anybody know what AMO stands for? Any guesses? No. Atomic mesoscopic optical physics. So, please. See if I can get the lighting.
I did put the city name as Boston on purpose. I'm glad someone noticed. All right. Thank you very much for the invitation. It's always nice to be in Boston, Cambridge area. It's nice to be in the new Cambridge. It's nice to be in Harvard. I have a lot of friends here, a lot of colleagues. So it's nice to spend usually more times, except this time, because of teaching requirements before and after the trip, I'm spending 19 hours time in the city I like. But nevertheless, I'm here today, so that's good. What I'd like to do is, given that there is dramatic overlap in some parts of our work with what goes on here, if you don't know, we call this the Boston phenomenon. All the Harvard, MIT, and others that work in this area, especially the solid-state quantum optics part, together with cold atoms part, it is, from looking from outside, at least from old Cambridge, it does look pretty impressive place to be in. So it's always nice to be here to share results. So I'll try to minimize the results that you would probably see, and I'll try to show you some results that are not necessarily interesting. Let's see. So again, this is to say what we do in our lab. It's basically a mixture of quantum optics toolbox that we use, developed earlier with some additions from MR and here and there. And we try to understand a bit solid-state physics if we don't know the material well. If we know the material well, we kind of sit to this side and we try to build up some small, very basic rudimentary concepts with quantum information or quantum networks. So overlapping strongly with what goes on here as well, you see that depending on how interesting the results are for a particular experiment or for particular results, we hop back and forth between our different hats of interests. All right? That's part of the research group. So I can show you some of the faces you might know already. That's Carmen, that works on 2D materials, and you see some others as well. And this is Clemens that worked on self-assembled coordinates, which basically highlights, and then this is Ben that works on SIDs. Just to give you an idea of individual people that work on different projects, the names will resonate with some of you. This is what the lab kind of looks like, one of the labs. We have cryostats and optical tables, similar to all of the labs here that work on similar topics. This side is silicon latency side in diamond, and that side is self-assembled quantum dots. So today, I will talk about self-assembled quantum dots, so it's all work that goes on over here. And just to highlight some of the materials we like to work with, the indium arsenide semiconductor quantum dots have been the workhorse since we established the lab. And then we have nitrogen vacancy centers and diamond we're working with, mostly nanodiamonds, but over here we also work with silicon vacancy centers and perhaps other color centers as well. And now we have some couple of newcomers into the system. Not so much the silicon carbide, we toy around with it, but mostly we're focused on the 2D materials. So there's almost like a lineup of how much we know about a particular system. So what I want to do is, today, with the time we have, I want to talk about these two systems. One where we know a lot, and in the second system we know very little. So that will also determine how I can answer the question. All right, so I want to start with a basic concept. So the first thing I want to show regarding the self-assembly quantum dots is creating quantum correlations between the spins. And the whole concept again goes to this. Of course, some of you in the audience, again, it's nice to be here. There will always be, whatever you talk about in Harvard, there will always be some expert in the audience that knows what you're talking about, almost better, in some cases even definitely better than you. So we have someone like that here as well. So, but the main concept I want to talk about is creating correlations and creating interactions between objects. So typically, forget about any applications. The main concept is that two objects need to be close, and we need to bring them to proximity so they can interact. So the whole concept of interaction is that objects are physically close, so that they can get interaction with. So that means that defines a certain length scale over which we have to bring these objects close, so that something like that happens. It's a universal sign for interaction, any interaction you want. And after that interaction, these two objects that never interacted before, after the interaction they can go their way, so that they're not interacting anymore. But if that interaction is a particular type, doesn't have to be, not always the case, but it's a particular type, you can actually sustain those correlations even though they have long gone far away from each other. And that, by the way, is the universal sign for correlations. All right? So this is obviously the concept of EPR, right? This is the EPR paper. Two objects and interacted at some point in time and then separated again. After they were separated, there are some correlations left or remaining between them. But the key thing is there is going to be, you have to select the right interaction that generates these correlations between properties of these two globes. You also have to make sure that you bring them close enough so that those interactions happen. So if I give you a couple of examples, depending on what these two objects are or what internal property of these two objects take part in that interaction, determines a particular length scale over which you need to bring them close, so that the interaction is strong enough so that you can create this kind of correlations if it is building back. Once again, correlation doesn't have to emerge for every kind of interaction, but it's possible. So you can have some sort of charge or spin-related interaction, and that defines a characteristic length scale. And then there's the third option. And the third option is, what if these objects are interacting through exchange of light, exchange of energy? And of course, the talk before was very nice for that purpose, because that is the whole idea, that if you have a bouncing energy between these two, you can start talking about creating some interaction. But then the question is, so how far apart should they be? What is the characteristic length scale for them? Right? And the nice thing is, if you are working with a well-defined optical mode, then you don't have to worry about R1 minus R2 directly. The exact location of the two objects no longer need to be immediately relevant, as has been in all these cases. So here what you need to make sure is that these two objects couple to one mode, well-defined optical mode. And if that's the case, then you can effectively create interactions between these two objects through that mode. And that's the whole principle of the waveguide concept, or two atoms in a single optical cavity concept using neutral atoms, and vice versa. So this basically says you can take these two mirrors, very picturesque view, and make them as far as possible you want, as long as the coupling to the mode, the well-defined optical mode, is present for both of them, the exact locations of the atoms are there. Now, all of you know this. But the reason I wanted to say it is because, isn't it nice that we can take out the concept of proximity for interactions simply by using light that is exchanged between, or energy exchange between objects. Sorry, so we can eliminate R1 minus R2 type behavior that exists in all other types of interactions with it. Now, where is this useful? Of course, this is the well-known image. It's used a lot. And basically, it highlights the concept of quantum networks. And the fact is, if I can create by energy exchange between two objects directly using light, then I can have what we call a quantum node, some box of some sort, another box of some sort, and some red arrow that links the two. Great. So all you need as an experimentalist in the lab are these boxes and the red arrow. That's all you need to know to build a quantum computer or network. The red arrow we can kind of guess it's going to be light, roughly in the near IR, traveling in the direction of the arrow, but presumably backwards as well. And then these boxes have to be something that has a certain property that allows them to be quantum nodes. Of course, Jeff Kimball went on further to show exactly how this is possible, what these boxes could be. And these are indeed single atoms in optical cavities, coupled by some sort of an optical mode. It could be waveguide, free space, whatever you want. And being able to couple two of these atoms being identical and coupled through a nice clean optical mode, you're able to create this kind of interaction. So I'm going to put down these two. Basically, the atoms have to be nice and clean in terms of the two levels that you can define, which are Cupid. So you can store a quantum state in these individual locations, in these nodes, and the optical link between them has to be clean. So this is another universal sign of depacing. It's a blue little wiggle inside an otherwise red clean oscillation. Right? So we don't want these in our optics, and we want these to be good quality, so it sustains quantum state without losing. So just want to highlight two works on this that goes in this direction. One is the Gara-Rempes results, or the Munich results, where indeed it's actually one-to-one. You can almost see that. This is an optical cavity in an atom, optical cavity atom, and there is a waveguide, optical fiber that couples and so nice oscillations in there with no wiggles. All right? And they've shown indeed that you can transfer states and entanglement. The second concept is to take this notion of proximity to an extra level. First, we didn't have proximity anymore, and we could create correlations between two objects. And next concept is, let's not even exchange anything between these two objects, and nevertheless still create correlations. So here, it's not that these two objects are far apart, but nevertheless coupled, create correlations through exchange of light. Let's make sure that they emit light, but they never actually see each other at all, and we end up with correlations. And that's through detection or post-selection. And the concept here is actually trying not to find out about things. Normally in physics, we try to find out about things when we make measurements. Here, you want to make a detection, but you're trying not to find out about where the photon might be emitted. So let's take the case where you're both trying to excite these two systems, and they may or may not emit photons. If they don't emit photons, nothing happens. 0, 0 means nothing, because you're sitting out here trying to detect a photon, for example. If you do emit a photon, it could be from this one or that one, you don't know. And as long as you can't tell, that's good. It leaves behind an uncertainty, a fundamental uncertainty of where the origin is. So to do that, one of the most powerful tools in quantum optics is the beam splitter. And you can use that. And by simply mixing the paths, and just by looking at these two outputs, limit yourself to only those emissions. Then, if you're able to see a single photon, you will be able to say, unless you know where they're coming from, for various reasons, where that photon comes from, you'll be able to collapse the system to a correlated state, essentially, without ever exchanging light between them. So in a way, you are doing a configuration type experiment to create these correlations. You want to see a photon, and you definitely don't want to know where it came from, and nor should anybody else. And for that one, the beautiful result, of course, comes from in the centers of diamond. Right? And there the idea was exactly that you scatter photons, as long as you're not able to tell where the origin is, but you know it was one photon, you can then correlate back. There are various different versions of realizing this measurement-based entanglement, but this is still one of the landmark experiments. There you go. Understood. All right. What I want to talk about, as I said, is the material we work with is self-assembled quantum dots. So we wanted to see if it's possible to do something like that as well. So that's the first story of the talk. Now, self-assembled quantum dots are essentially essentially they're terrible quantum wells on top of gallium arsenide. So you grow gallium arsenide in molecular beam epitaxy, and then you say, great, now I don't want to grow gallium arsenide anymore. Now I want indium arsenide layers on top, a heterostructure. So you start growing indium arsenide. If you don't pay attention and you grow a lot, that's fine. You get big bulk indium arsenide with some dislocations at the interface because the lattice constants don't match. So there's some strain and stress involved at that interface, but it's relaxed quickly, and then you recover nice clean semiconductor. But if you pay attention in the very beginning stages, between one monolayer of indium arsenide, which is forced to have the same lattice constant as the gallium arsenide below, because it's so much more dominant, versus two, where it would start kicking in, or bringing in its own lattice constant, there's a mini phase transition. It's actually 1.6 monolayers. That very thin, stretched layer becomes little bubbles, droplets, all of a sudden. And it actually looks like this. These little bubbles, doesn't really look exactly like a bubble, but kind of like a bubble. The key thing I wanted to highlight is that if you look carefully, these are individual atoms, about maybe 100,000, between 10,000 to 100,000 atoms forming this bubbles. They have very nice crystalline structure. So it's not like just a ball of atoms lumped together like a liquid. It is actually a nice, clean, crystalline form. That's why self-assembled quantum dots, these guys, possess the actual bulk properties of their host materials, the indium arsenide and the gallium arsenide. So the lattice structure that we know from bulk actually still is sustained, and therefore optical properties kind of have those properties carried forward. But they're roughly 20 nanometers in diameter and about 2 to 3 nanometers in height. So they're like small pancakes, little disks that are on top of the surface. At that point, you stop growing indium arsenide, and you say, let's continue with gallium arsenide again. And you cap the whole thing so that basically you have this layer, kind of looks like, feels like a delta doping of quantum dots. You have this fixed layer of randomly located these islands, these quantum dots. They were first used for device physics. They had nothing to do with quantum information, but spins confined, a single electron spin confining these quantum dots was first proposed in 1998, 1999, I should say, for the self-assembly part, in this very nice paper, actually I work with. Now, if you look in this paper, you have to be careful. As an experimentalist, you probably would never want to do this. This is they suggest how to do it. The idea is you have all these randomly located quantum dots in a microdisk. The quantum dots each have a single spin, and they're at random wavelengths, because they emit at different wavelengths, there's a big dispersion, and they're in this cavity defined by the whispering gallery mode of this microdisk. Fantastic. So all you have to do is take this guy, this one, and that one, for example, that normally wouldn't talk to each other, because they're too far, it's about 3-4 microns, and bring them in resonance with the cavity mode, and then they talk through cavity. They exchange energy, effectively, through the cavity mode, and then you have that coupling, that interaction that we're talking about. Same concept as the cavity mirrors and two guys similar. Now, and what they suggest is that, of course, they suggested 4 near-field tips. How many of you have done near-field optics? How many of you have done 2 near-field optic tips? They suggest 4, as an example, each one having a strong laser for stark shifting, optical stark shifting the resonances to the common mode, so they can interact, plus auxiliary lasers for the readout and preparation and all of those. So each one has multiple currents going in, and you're supposed to have everything happening on a 5 micron square. So obviously you're not going to start doing these experiments. But isn't that great that referees allowed this paper to go through? Because in 1999, even though it may not be feasible, this is still what we're trying to do. Right? You have a single mode defined, and you have multiple systems, quantum nodes, if you will, coupled to that one mode, and they interact via a common optical mode. Doesn't matter how big or small, the concept is there. So already in 1999, the optically linked distant, otherwise distant nodes concept was there. Technically, everything we do is pointing to that direction as well. And as I said, they are sufficiently complicated and dirty systems, but also clean systems when you want them to be, so you can flip-flop your hats as you like. So how do we work with these devices? We don't work with them bare. We actually put them in contacts. So these are these layers that sit there. And then we have an endope layer underneath, so it's an electron reservoir. And then we have a thin Schottky window above. And the whole thing is around 150 nanometers or so it's very narrow. And then by applying a voltage, you can basically tune the energy diagram of this whole system, almost like a lever arm. So with the voltage you apply, you can either deplete any electron in the conduction band, or you can allow one electron in if you apply the right voltage. That range, where there is, from one end, you have no electrons in the quantum dot, and on the other end, you finally have 2 electrons in the quantum dot, due to spin degeneracy, for example, but enough energy given to the quantum dot to fight the Coulomb repulsion. The capacitance is very small. That range is about 150 millivolts or so, so it's very comfortable in the lab to actually be in that single electron occupancy regime determinism. And once you have that, of course, you have these 4-level systems. So that, for us, that brings us to the atomic type approach, and then we don't have to worry about the rest of it until we get a Rho-Platon coherence or something. But the main thing is the ground state is spin up and spin down. For the electron that is trapped in this configuration, and the excited state is that electron plus an extra exciton, or the whole thing is called a neutron parameters. And you have spin selective transitions. This is what it looks like. So that's the chip of gallium arsenide with a layer of quantum dots embedded. These are the contacts, these guys. And right on top of it is one big blob of solar immersion lens. It's a hemisphere that's literally glued on top of the sample. That's our fabrication capabilities at the moment. We can do waveguides, we can do other stuff, but anything we do with these self-assembled quantum dots reduces their quality. So it turns out that for most of the experiments, by simply putting a hemisphere of zirconia on top worked for a without show. And if you look through this blob of zirconia, it's massive blob, you get to see these Schottky barriers, this thin layer, it's about 6 nanometers in thickness of titanium. And if you zoom more, you see these quantum dots, and if you zoom in one, you verify that it does emit one photon at a time, and now you're ready, you characterize your system. And it turns out, with these quantum dots, the quantum yield is very high. The mode matching due to the solar immersion lens is reasonable, matching the energy of our objectives. So in a bath-dry-stat operation, coming out of a single mode fiber at the end, we're operating at around 8 million photons per second. The line width is about 20% broader, 30% broader than natural line width. So these are very clean systems if you find the right sample. If you find the wrong sample, count rates drop down to 10K, and the line width is a couple of gigahertz. So it depends on how good quality the wafer is, the original gallium arsenide wafer is. But it is possible to have reasonably clean systems. All right? So that's why, coming back to that, it justifies that for us, for the experiments where we need the strong counts, 8 million photons coming out is I'm happy with that. So we need to control the spin. For that purpose, we have yet another expert in the audience that has done spin control. Again, anything I'll talk about, there will be one other person who has done that in the past. Normally, you would couple directly to the magnetic, you can do magnetic coupling for the spin state, but we use optics. We use the excited state to do stimulated Raman type transitions, which makes things very fast for us. So instead of typically what we would get, direct coupling is on the order of 10 nanoseconds or so to be able to do a full swap, we're able to do it in 3 picoseconds. So that gives us an extreme fast time scale for doing spin rotations. And the spin echo, if we do a spin echo on the electron, a pi over 2 pulse, pi over 2, and read up, we're operating around 3 microseconds. Now, this is the fundamental limit. We can't get better than 3 microseconds. So anytime you talk to any quantum dot people, they'll say, yeah, it's on the order of 3 microseconds, but that's it. It's fundamentally dictated by the strain dispersion experienced inside the quantum dot, affecting the quadrupolar couplings of nuclear spins, in turn affecting the electron. Okay. So it is complicated as a system, which is fun to study as a physics problem, but it's terrible if you want to extend it. But what this says is that 3 microseconds is all you have, and don't even try dynamic decoupling, essentially, for this purpose. just to highlight how difficult actually just to do the spin echo part, this is what spin echo, raw spin echo data looks like. So if you take this data and take it to your supervisor sends you back to the lab and say, or no, sends you to the library and says, look up what spin echo signal looks like, and don't bring me this. It looks like anything but that. And the reason for spin echo looking like this is because we don't have a single spin with some boring dephasing that's taking place. We have a nice clean spin coupled to a spin reservoir of about 10,000 nuclear spins to 50,000 nuclear spins, and you're polarizing them. They're in direct contact interaction, and over a long time scale, but short compared to the length of your experiment to sweep, you're actually continuously polarizing the nuclear spins. So the reason you see this is because it's a massive feedback system of nuclear spins being polarized meaning shifting the Zeeman splitting of the electron spin, and therefore your optical transitions shift. So the phase you acquire is different. So the whole thing tumbles as you try to optically act. So you have to sort all of that out to be able to get a clean profile. And the way we do it is that basically, poor man's version, the simplest thing you can imagine. You basically, you do your whole operation with alternating with a 0 or a pi pi flip before and after. So you keep trying to polarize nuclear spins one way, in one shot, and then the other way, in the other shot, this way, one shot, this way, other shot. So you never build up nuclear spin polarization. That's our trick. So all the experiments I'll show will have this in the background, that there's an alternating sequence. And then you recover the spin echo signal, and then you get the 3 microseconds. All right? Clean if I want to, dirty if I want to. Good. Let's come back to this. So now that it's back to clean, we now have a Raman scheme that we can consider for each of these cryostats sitting side by side in the lab. And then you draw one transition and you emit photons, and you want to check that you can't tell the two photons apart. That's how good the photons need to be. Before that, of course, you need to make sure that all the transitions are the same. And what you do is you apply to electric fields, magnetic fields to make sure they're the same. Example would be Ramsey fringes for each quantum separately to make sure that we match the ground state splittings identically, because they wander off as time goes by. All right, so let's do the optical part. All I need to know is, or all I need to achieve is not to be able to tell the difference between one photon from the other. And of course, for that one, you need Hongo-Mendel type interference experiment. And if everything goes well, the 1-1 term disappears on the other side of the beam splitter. Again, beam splitter is the magic element. So I have all of these to match. And if you look at some selected list of experiments historically, you'll notice that depending on the method of excitation, you get different percentages of indistinguishability. The first one is 18% indistinguishable, 82% distinguishable. It's almost like that you wanted to be distinguishable, but you failed 18% of the time. Right? This tells you how difficult the whole journey was on the non-resonant excitation. You use the higher lying state to excite, and then you wait for a decay, and then you get the optical photon that comes out at the end, and you look at how reproducible these photons are. The best was 52% in the absence of any cavity enhancement. So again, I'm not showing any cavity results. They are good because you're broadening the transition by herself, and that helps eat away these spectral fluctuations that you might have in the system. So that's a problem. We're not going to be able to say, I don't know where the photons came from, because I have no idea what to do with the 50%. Well, so what you need comes from an energy drink. The photon is an energy drink, apparently. Those are the two properties we need. The first one is pure energy. That I think we all agree. It's kind of automatic. Photons don't have mass. And the second part is pure perfection. That's the part that's missing. It's almost like the first one is automatic. The second part, unfortunately, is the missing bit. So why is it missing? It's called spectroscopy. It's missing because our usual way in all of those experiments as well, the usual way we work with is we go up to an excited state, we live there for a finite lifetime, and during that finite lifetime, whatever your object is, say in this case exciton, your exciton looks around and probes the environment. close to the environment, learns about it. A charge trap is emptied over there, another one is filled over here. Each one has a consequence to the energy state, to the energy of the x at a time. And if you map it as a function of time, for example, you can get a nice view of that environment, local environment, its time scales, the magnitudes, everything that's going on. And this actually, I think, is from MB. I'm just putting it out there. But not everything is good. But this is exactly the point. I don't want this in this experiment. I want the photons to be identical. I don't want to know about the local environment. That's hardly the motivation for the correlation, long-distance correlation experiments. So what I want is this one. All right? I want a trampoline as my quantum dot, where I get a photon out. I get that kind of a photon if, for example, the internal state is A, and I don't want a photon if the internal state is B. But I don't want the photon to tell me anything beyond that. So the example I usually give with this one is, if you have kids, when you throw your kid on a trampoline, I have kids, so I don't know. I'm told. So if you throw your kid on a trampoline, your kid comes and jumps off on the other side. You don't want the manufacturer details on your kid's face jumping off the trampoline. You want your kid to be exactly the way you sent your kid to the trampoline on the other side. No change. That's how I want my photons. I want the photons to come out as I wanted in the first place, independent of the trampoline, only dependent on the state of the trampoline, whether it's there or not, for example. I won't carry out the So there's a very simple answer for that. And the simple answer is actually elastic scattering. So if you're operating in a regime in pure quantum optics where the interaction, your excitation with light is not too strong, then you can operate in this regime where the scattering is dominated by elastic scattering. The light generated is mostly elastic. What does that mean? It means you're not actually constantly going to an excited state and then waiting for a decay. You're actually scattering a laser photon into the environment, into other modes, without really changing its properties. There's fine-tuning in there that I'm skipping, but essentially you get something that looks like a laser and walks like a laser. Okay, so that's good, that's encouraging. So I'm getting laser photons back as elastic scattering. Maybe that could be something. So if you look at this, this is as a function of excitation power versus fluorescence intensity. You have two components, the incoherent component, the blue, and the coherent component, the green. The black is the excited state population. So you can reach half that in steady state. And basically what it shows is that if you excite the system at rather strong levels, the spectrum of light that's emitted by a single atom has a modal triplet profile. It has ears due to the dress states, the strong coupling that you have with the laser with the system, and you get a bit of component on top that looks just like a laser. Just to make it clear, the laser, residual laser, leftover laser we couldn't move in the system, is down here. That's the residual component, its power. The rest is actually coming from the scatter. And then if you tune below saturation, or right around saturation, now you get this sharp feature, and then you get a single Lorentzian underneath, not as strong, but still finite. And if you go further, even that component disappears. You're left with a very sharp feature, which corresponds to the screen, the elastic scattering component. So even the spectrum of light coming from a two-level system looks just like a laser in the weak excitation, or relatively weak excitation. Now, this is where, usually, there are three groups in the audience. One group is from solid-state spectroscopy that says, what? What do you mean two different types of emission? The other part is atomic people and say, yeah, of course, but that's classical. And then there are the people in between who know everything about this, who figured out that these are not neither classical nor what are you talking about. They are there and they are anti-bunch. Right? It doesn't matter which level you're in or which excitation regime you're in. The atom can't scatter more than one photon at a time anyways. So while all this complexity still shows up as an anti-bunch one photon at a time, on the other end, what looks like a laser and propagates like a laser is still anti-bunch in the sense that it's one photon at a time. So it's single individual laser photons that are scattered. And that one, I should say, That one was first seen, this concept of coherent incoherent components was first seen by Herbert Walter on trapped ions, and he called it the wave particle duality, which I don't need. Anyways. But never mind, to disagree with Herbert Walter. One time when I was giving a talk at Munich, Herbert Walter was in the audience. Passed away now, so 5 years, but he was in the audience, and at the end of the talk he asked me how long do quantum dots stay where they are without being diffused into the lattice and disappear. I think it's kind of the lifetime of the universe. It was an interesting question to answer. All right, what I want to show here is the only reason we did this experiment in the first place, the coherent versus incoherent component from a quantum dot, was because there was, at the time, 3 years ago, there was a big discussion in the community on whether there is fast dephasing or not in these quantum dots. Spectral diffusions, yes, but do we actually have sufficiently fast dynamics that dephase the quantum dots that broaden the transitions? Because not many people were seeing very narrow lines. So we said, again, going back to the toolbox for quantum optics, this feature, the coherent versus incoherent component ratio, that's laid out nicely here, only works if you don't have fast dephasing. If you have fast dephasing, the coherent component starts to die off. If you have a lot of fast dephasing, you might just not see it at all. It might completely be lost. Because the whole thing relies on creating coherences between the two states without scattering photons in the first place. If within a lifetime you're already decoherent, that term that allows you to have elastic scattering is gone. You won't see it. So the only reason we did this experiment was to figure out how much fast dephasing exists in the system. And turned out we can't really tell. We couldn't, the upper bound we could put was negligible. I think that was the upper bound. So we couldn't really tell how much fast dephasing exists because it looked very much like a two-level system at the time. We have spectral diffusion, but we don't have a very strong fast dephasing, which made it interesting. And then just to show that what scattering is really, really like a laser, you do a simple heterodyne experiment where you take your laser, split it, frequency shift it, and then when you combine the two lasers, you should get a beating at the frequency difference, and the width of that beating when you do a Fourier transform is going to give you how coherent they stick together, right? Here, instead of the two arms of the laser, now you put in static quantum dot, so what is scattered is one photon at a time, but interfering with the laser, and we're able to get something sub-hertz. It doesn't mean the emission from the dot is parked to a particular absolute frequency, it just means whatever the laser is doing, the quantum dot scattering is going to follow. So that's neat. That means if you have multiple quantum dots you're exciting, you can have one laser that's moderately stabilized. You're driving everything together. The photons that they scatter from this common laser will be all locked to each other, just like they're locked to the laser. And of course, if it looks like a laser, walks like a laser, and propagates like a laser, then what is different? The difference is indeed the combination that it looks like a laser in that sense, but it is anti-bunched. So you actually have some coherence with the vacuum in that sense. As in, you don't know that you're emitting that photon. You don't get that. You don't get this state when you know you've scattered a photon. It is fundamentally a probabilistic scheme, and you don't know until you make a measurement that you scattered. That's why you're able to write it as a superposition state, which is. I'll skip this quickly. We use those kind of scattering photons to actually couple trapped ions and quantum dots, which have dramatic, let's show it here, with Michael Kill's group, which have dramatic line widths. So two systems that don't like each other, technically. All you need to know is these units over here. One is in terms of megahertz, one is in terms of gigahertz. This is amazingly narrow for quantum dots, fantastic, and this is incredibly broadened due to cavity, which is otherwise kilohertz range. So, but despite that, this is a big mismatch between the two, and we're able to get quite reasonable coupling, almost as strong as a laser in this system. Yeah. So if I were to take a single laser and drive the ion, I can see the transitions, I can saturate the ion. If I do the same thing with single photons from a quantum dot, we could also saturate the ion, even though the spectra don't match at all by factor of 1. So that's where immediately you can think of using these coherent photons, elastically scattered photons, to link multiple systems. Okay? Now I come back to this. We want to use coherently scattered photons but in this Raman scheme. So now it's not so much that we're limited fundamentally by the laser, but also by the ground state coherence. So the quality of the photons will go down now a little bit, but hopefully not too much. But nevertheless, it's the same idea. We drive this system weakly, and then we scatter a Raman photon, and then try to see how well they interfere. So that's first G2. So it's different than what we usually do with two-level systems. We don't just go up and down, up and down. Here we drive these systems and then emit a photon. But then the system is shut. Even though you might have your laser on, nothing happens. So you have to pump it back, which is, again, normal for atomic people. But in semiconductor physics, we don't pump it back. You wait a little bit and decoherence and everything's back to where it's supposed to be. So, but here we actually have to generally pump it back and then do the whole experiment. And then you actually don't get a vector, simply because there's nothing to emit. Only dark noise, essentially. And then if you do interference of those two, where you postulate the cases where both emit photons, then the interference is now at least accepted in terms of trying to do these experiments. This is essentially a Hongo-Mendel dip, and the visibility becomes 93% of one. Again, interfered a long time, no filters, it's just photons as they come. And what is interesting, I wanted to highlight it here, not to say, oh, we can be better, but only to say that if we do a time filter, think of the wave packet coming out. These are shaped pulses driving this transition to scatter these photons. As I said, the quality of the photons is dictated by the quality of the ground state, coherence. So it turns out that if we slice off the last bit, the remaining end tail of the photons, the quality goes up. So you see that the time evolution and the decoherence that comes up when the ground state maps itself onto the visibility coming from two independent quantum dots, because it's ultimately limited by T2 stuff. You can do T2 to protect it. In these experiments, we don't for the proof of principle, but that's ultimately gives you a change of time scales. Anyways, let me go through this part. So once you detect the photon and don't know where it came from, you want to go back and check what the spin state is. So for a single quantum dot, we can tell, we can find a correlation between where we find the internal state of the quantum dot with having detected a photon, whether it's still here, down, because we didn't see a photon, or up when we did see a photon, if you will. If you do that experiment, then that also puts a below 100% limit. Yeah, that's another prefactor that will be multiplied, minus 7%. And if we do two together all at the same time, look at that. With such a state being more or less prepared, most of the time nothing happens. Sometimes you detect a photon and you end up with that kind of a state, anti-correlated spins, because only one flipped. And with some probability, you also have a case where both flipped, and then you get a PP. Oh, sorry, you get an up type of case. And when you do this, let's see, the Z basis is 90 or 86. I'm gently reducing the numbers to lower values. We're now in the Z basis, which is, you can call it the classical one, in the sense that classical correlations would have existed here as well. If they're supposed to be anti-correlated, that's how well we can tell what's going on. But the key thing I wanted to show here are these two features. The first one here is that they have to be more or less the same in your experiments. Up, down, and down, up are not automatically the same. If one quantum dot emits brighter than the other one, I have fundamentally inference that most likely it's going to be up, down, rather than down, up. So I need to not have those states. I need to make sure the two dots not only are identical, they also emit identical number of photons, the probability. Now, you can imagine what happens in the lab. Your student comes in and says, yeah, this Christ, that was 6 million, the other one was 5 million, so we reduced that one down to 5 million to match. And yes, technically that works, but you kind of want to say, how about bringing the other one to 6, so that they're both 6? Sometimes you actually have to do that. Sometimes, for stability purposes, you actually lower both counts to match exactly the same. The second thing is this bit, and that is indeed this two-photon case, that we expect a fundamental error in our measurement, our correlations, simply because we know by the power that we're exciting, we will generate a few percent of these wrong correlations. The up-up will be there because there will be 2 photons emitted, even though we don't resolve the photon number, essentially. So this is a bit of a calibration for us as well to check that we're operating the right. And then finally, the X basis, where quantum correlations kick in, we're down to 40%, roughly, of correlations remaining in the X basis, where decoherence really kills you. This is the most fundamental axis. And if you combine the two, we're operating around 63%. Let's see, in terms of quality of the correlations we can check, we can verify between these two systems or self-assembly models. Now, of course, coming up to this again. So reasonable, 60%. How many of you think 60% is good? How many of you think 60% is pretty bad? No one said bad. It's okay, I'm not offended. We can say it's bad. But we'll see, I'll show you another slide. But before that, I want to show you something else. To be able to even see the 60% or the 40% in the X basis, you have to do something. You have to actually stabilize this whole thing. You see what's happening? Laser comes in, splits into 2, goes inside a bath price that's sitting over there, hits a sample, semiconductor, comes back to a silk, comes back out into a single mode fiber, goes to another setup, another optical table. There are a few more elements than just the beam splitter. And then the detection setup, which happens to be this like a space, another setup, another table. Same thing happens to that side. And if the scattering is coherent, this whole thing is one big massive interferometer in 2 cryostats in and out, table. Right? So you have to stabilize all that to get any signal at all in terms of phase correlation. So we had to do that. But in the process of stabilizing, which took a long time, but it worked, process of stabilizing, you realize, that phase that you just stabilized, it contributes to that, the relative phase of the spins. Everything contributes to that, unfortunately. That's why it's not easy to see. The mismatch in the splittings, ground state splittings contributes to that. The wavelength slightly being off within the bandwidth contributes to that. But also the boring external parameter, the interferometer stability also contributes. So basically, by having stabilized it now, you can literally, by changing a PID controller, you can tune the phase of that interferometer and actually see the change of the state you're left with once you make a measurement. You can tune it. Not only you can keep it to one state, but you can tune it from one to the other. And if you include local operation as well, you can generate all 4 best states by hand. All right. Now, here comes the big question. If all these papers plus more, it's not all of it, if all these papers plus more have done this already, why the hell would you want to do it? Why do you want to be number 10 if these papers have already shown distant correlations? Well, the answer is, we think, and Atature also thought as well, with the whole spins, we thought that self-assembled quantum rounds offer something complementary to the other systems. To show you that, see if you buy it, we have a nice plot of Bell state fidelity in the correlations we created versus entanglement generation rate. These are the 9 papers I've highlighted. There are a few missing in there, here and there, but first of all, there's a general trend. So you don't get, you don't win. There's no win-win, you win or lose, depending on the axis you choose. These are the amazing the results, and you can see that they are not beaten by any system. This is our result. So we have the highest rate. That's one parameter you can pick as a storyline. We're operating at kilohertz rate of generation. And the other thing I wanted to highlight, how many people in the audience are working with trapped ions? Is there anyone? Good. Oh, really? Okay. Sorry. Because what I want to say is, if you look at number 3 and 6, these are trapped ions. So we're not too bad. Now, how many people think 62% is terrible? Good. That's the right question to ask. So the main problem is, none of these are actually very good. I mean, the whole point is, if you want to extend it to quantum networks, these have to be all, they should shoot all the way up there instead of in one. So in that sense, in these have the capability for the fidelity, although they suffer from the rate. None of these are fundamental limits. They can be extended, but they're just snapshots of the community. But you can imagine now with this very large distribution, how many octaves of rate distribution, you can start thinking cases where you want to store information for a very long time due to spin coherence and long distance coupling of individual objects. You're aiming at a particular type of physical system. And if you're interested in on-chip few spins that talk to each other, for example, a cluster of spins that talk to each other, and if you consider the time it takes within the coherence time of these quantum dots, that we have about 200 to 300 meters of beam propagation, light propagation, where the correlations are preserved. So you can easily think of an on-chip arrangement where quantum dots act as entanglement generators that feed the system, the fast rate, fast beam kilohertz. But there's a more bleak story. The more bleak story is, let's not worry about the rate at which we generate entanglement. Let's worry about the probability you generate per shot. You try, and what is the probability that you actually get it? We're still not bad, although transmons beat us a little bit. And again, there's a big variation of the x-axis, but unfortunately, 10 to the minus 2 probability is too bad. It's not good enough. So regardless of the physical system, we have a problem that we're not efficient enough to push to the regime where each attempt actually gives you something. It doesn't have to be unity, but it has to be a few percent at least to start talking about possible scalable concepts. And overlapping nicely with the work that goes on here as well, the concept of waveguides actually is perhaps one solution, because the rate at which you can expect light is a key problem. At least within on chip, not necessarily coupling out, but at least within on chip, within the chip, you might be able to push these systems to megabits for self-assembled dots or other solid-state systems compared to perhaps some other alternatives. All right. So hopefully I said reasonable fidelity, but high rate. I hope you buy it. So I'll finish this section with basically just highlighting the 3 time scales, or 3 rates that relate to the self-assembled quantum dots that you need to know about. And what we want to do next is to utilize the main strong point of the self-assembled quantum dots, and that is the topology of the photons that they emit and the rate at which they emit. So we are going in the direction of more cluster state, and also not only 1D from a quantum dot, but also entangled quantum dots collectively generating clusters simultaneously in 2D. So that's where we are going with the self-assembled quantum dots. Now with the remaining few minutes, if you're all right with it, I'll tell you a bit about the 2D materials. Is that all right? Do I have 10 minutes? 5, 10? Okay. So there you go. That's a commonly used image for self-assembled quantum, for many materials. I gave the example of a molecular beam epitaxy and how it's used for self-assembled quantum dots and heterostructures. Molecular beam epitaxy people go home, and then they sleep, and in their dream, they see this. They're dreaming, and they're thinking, layer at a time, one layer grows, but only one layer, and then the second layer comes, and then the third layer comes of arbitrary atoms and formations of monolayer crystals. Anything you want. You get whatever you want, hidden or close. All right? And it's even more interesting that you don't need molecular beam epitaxy for this. You literally need sellotape to get maybe slightly more advanced now, but you just slap one on top of each other and it works. So obviously it's very interesting system, and it gives you many options in terms of properties, anywhere from semiconductors to semi-metals to superconducting systems and insulators. So there's a wide range of materials you can explore by simply slapping them on top of each other. And they do emit light. Those that emit light or radiation do it over a very, very large scale. So it really gives you immense flexibility to toy around. And from a physics perspective, it's always interesting to say, okay, well, I have a material that is single atom thick. I don't even know what the exciton is. Is it a multi-exciton or many exciton? It would be interesting to study these things. Very recently, last year, 4 papers came out in one Nature Nanotechnology issue. And I say this always, this is one of the most boring issues you can have for Nature Nanotechnology, because once you read the first one, it's the same one, it's the same paper. I worked with Atature Nick worked with me as a postdoc. Chao Yang was my PhD student. So obviously I can't skip a generation. I had to start working on this as well. This is interesting because that actually is written in a different format. So you can see there how we influence each other in writing the same type of papers. So you'll see the same words appeared in these three, but this is written differently. We never work with it. But anyways, what they reported, all four of them, is that these flakes of materials, WAC2 or whatever you have these confined excitons that emit one photon at a time. It's kind of like the quantum dots. So, and the problem is we said, okay, well, let's do it too. Let's see if we see these guys. So we tried to do it in the lab. We don't see them for various reasons. And then it turned out that students who are very careful making these devices just don't get to see the quantum dots. Students who are kind of sloppy, I don't want to name anybody, but students who are sloppy, I just quickly did it, end up with a lot of quantum dots in there and they can study them. So clearly there's some issue regarding how clean or how careful a student is and not seeing any results at all. Beautiful results, but nothing, absolutely nothing in the flake. No emission at all in terms of confined states, if you're very careful. So we said, I'm going to skip this part. So we said, could it be because of local perturbations that lead to perhaps strain, that lead to these confined excitons? And there were a couple of papers that indicated this might be the case. So we said, okay, let's make structures with Marcus group here. And Paul is somewhere here. Such that we have these tiny needles, and then we can put these layered materials right on top. So instead of a nice clean substrate, let's say these needles, and then put the layers. And then let's see if we can induce extone confinement in these materials. And it turns out, when you do this, either you pierce, the needles are too sharp, so the material actually goes through, but if it doesn't pierce, then it tends like this. So this is an AFM scan of the needle plus the WAC2 on top of the needle. So you can imagine what's happening. Beyond here, the material is on the surface, but up here, these guys, this is a tent. The whole tip of the pillar is being stretched. The material on the tip is being stretched by the weight of the remaining parts. It's a tent. And so right at the top, we have a strong strain present. And if you do a dark field, then on this large flake, you get to see multiple. Each one is separated by 3 microns. So all of a sudden, even if you do it very cleanly, you end up having multiple locations to study for that purpose. So 30% in this experiment were pierced. The rest weren't, but it's about how well we press these materials. So I think we can improve on that. So when you do it, here's an example of 6 pillars in a row. And on each one, you get sharp emission peaks, and each one showing anti-bunching in return. And you see the data, which is too bright. But if you, in some cases, you see very nice clean symmetries coming from each perturbation. And what I'll show is that actually it gets better with pillar height. So the more the remaining material pulls by weight on the top of the pillar, the cleaner the quantum dot that is formed exactly at the top of the pillar is. And here what you're seeing is 2 very interesting features I would not have expected. One is you have 50% chance that on 95% of all the emitters that are exactly where you want them to be, it's only one emitter. So it's not that we have multiple emitters formed, but they're deterministic one at a time, 50% of the time. There's a joke with Anchorman movie. 50% of the time it's deterministic. It's exactly that. 5% of the time is nothing, 50% of the time is only one, and then it varies. The second thing, more unexpected one, is the quality of the light that comes up. Higher the pillar, cleaner the spectrum. The spectral diffusion is suppressed. This is same scale, essentially, almost. Yeah, it should be the same scale, that's right. This is for 60 nanometer pillar, 130 and then 190 nanometer pillar, really stretched, and then you have nice clean profile. And this is the spectral boundary. And if you do this on different materials like WS2, you also get again the same feature of being able to create these that will. So in that sense, again, very similar profiles. What it says is all you need to do to create these quantum dots at these locations is create a perturbation underneath. And we've done the most boring, but the most boring substrate you can imagine, silicon oxide. If you now have some sort of full man's version of tuning them, Marco is going to do that. That's right. Marco will take care of that. I'll just leave it to him. Marco, we want little springs. Or you do it on a different material like diamond, where each pillar, which you can actually implant, each active spin or even a dark spin coupled to the exciton that is monolayered away from it. So this is the next thing that one can pursue, to have a coupled system of these structures. And again, the question is, well, is it silicon oxide dependent, or is it can be any arbitrary system? And here is nanodiamonds, silicon oxide and nanodiamonds together. And this is the AFF profile. And if you look over there, with the flake on top of it, then we get the emission. So we can create confined exons, quantum dots on top of nanodiamonds, nice sharp emission peaks. Of course, that nanodiamond didn't have any spin, so this needs to be done more properly, but you see the concept. So the open question is spin. I don't know what these peaks are. They're confined excitons, but I don't know if I can get a tryon, if it's a pure neutral exciton. They are neutral excitons actually, but because we see the XY splitting. But the open question will be tryon and spin excess for these systems. So basically those are the next thing that we do. So I give you a snapshot of two systems, one that we know quite well and know how to handle and what it gives us in return. And the second one we know hardly anything about, and what opportunities lie in both of those. And these are the things that work. And I thank you for your attention.
For instance, very large optomechanical couplings, because for unit displacement, where you're suggesting the energy of the exciton is changing significantly, could this be like interesting for optomechanics experiments?
I have to be careful. The energy of the exciton, meaning the optical transition, let's say, varies dramatically from pillar to pillar. So we have inhomogeneous distribution, let's say, or a wide distribution of where the peaks are. The center wavelength shifts. The quality of the emission is better by taller pillars. So a higher strain, better quality, but the distribution per wavelength is still large. So this could be coming indeed from the fact that we don't really control the pillars too carefully. They're reasonable pillars, but we haven't actually studied shape of the pillars or size of the pillars. So, but nevertheless, the spread is large. So I would refrain from saying that strain can tune the wavelength. That I don't know yet. What I also don't know is how much strain there is. Until I do a cryogenic Raman, micro Raman, walking across the pillar and verifying how much strain gradient we have on site, I won't be able to tell you exactly how the band modulation happens to give us this confinement. But technically, yes.
Second question, did you apply magnetic fields to these transitions?
Not yet. We're doing that now.
Other questions? If not, then join me in thanking Mete.